All right, good morning, everyone. My name is Thorsten Kroger. I have the honor to chair the session, and the name of this session is, let me read this for you. It's Motion and Path Planning 3, Planning, Failure, Detection, and Recovery. A few organizational notes. I would like to ask the speakers with even numbers to sit here because this will be your presentation spot, and the speakers with odd numbers to be here for the left side. Lydia is speaker number 1, and the speaker number 2 can feel free to already get started here. Now I would like to introduce the keynote, which will be given by Professor Lydia Kavraki from Rice University. And she will have 20 minutes to talk about planning for complex high-level missions. And after that, we will get started with the 3-minute teaser presentations. Lydia, please.
Thank you. Thank you for the introduction. And good morning to all of you. It is really a privilege for me to be standing here. And I want to take this opportunity to discuss research that my students, collaborators, and myself have been doing over the last few years at my laboratory. And they relate to the theme of planning for complex high-level missions. We do have robots today. You will agree with me, they are getting better and better. The design is improving. The processing speed is improving, bandwidth is improving. Yet still, we are struggling with certain things that we would like these robots to do. And I'm going to focus on one of them. And this is planning, moving beyond the reach to destination paradigm. We're very good in the motion planning community in robotics to tell the robot, okay, go out of this room, fetch the ball and come back. But what if we have a higher level mission, like the one I'm showing to you here? We have a janitor robot, we have an office space, and we want to give a mission to the robot like the one I have written down in this slide. Do the following in any order. I don't want to specify all details. Always avoid the black demo area because something very, very sensitive is happening there. I want you to water the plant, clean the blackboard, turn off the coffee maker, pick up the vacuum cleaner for the supply room, vacuum the orange room, and dust its table. This is the level at which I would like to specify a mission, and hopefully the robot will figure out what to do. I'm interested in janitor robots, but I'm also very much interested in robots that will clean cluttered workspaces like playrooms, for example, for my children. The execution of autonomous complex missions is not a new theme in our field. AI started with this many years ago, robotics started with this many, many years ago, and today, as we look more and more closely into the problem, we do realize there are different aspects of this. For example, reasoning over tasks typically involves discrete reasoning. Reasoning over dynamics typically involves continuous reasoning, and everything has to be put together, and everything has to be made sense to be able to achieve high-level motions. And today, we have several participants in our community that have a stake in this problem, and they have different techniques to contribute, all of which are interesting for the problem. There is some overlap. I'm not trying to be exhaustive here, but AI brings, let's say, constraint satisfaction methods and associated planners. Learning has a huge role to play, both at the level of tasks and at the level of motion planning. Formal methods, and by this I mean verification, model checking, are playing an increasingly important role because we want to do things and want to verify they are done correctly. Motion planning, as we understand in the community, of course, has a role to play and control theory. And I just went to look at very, very recent literature in this topic, and we see a lot. In 2013, 2014, and this is by no means, again, an exhaustive list, we see a lot of papers at the intersection of AI and motion planning. We see the use of constraint satisfaction methods coupled, let's say, with sample-based motion planners, techniques that are pursued by several groups, including Peter Abill's group and Kepling and Lozano Perez. We see formal methods coupled with control theory. And here I'm talking about the work of Pablo Taboada, for example, where he uses formal methods to construct provably correct controllers, or the work of Richard Mary and Hadas Kreis-Gazit that have shown us how to use formal methods to construct reactive frameworks that have provable guarantees that are by construction correct for certain kinds of robots to execute tasks. And we are working here. We do not want to place any restrictions on what kind of robot we have. In fact, we can work with robots that for which we do not have controllers available. And we want to couple the kind of methods that we know how to work with, sampling-based methods, with formal methods, and see how far can we go in the execution of complex missions. So again, I like to be general in my work and think and develop algorithms that do work for systems with complex dynamics that may include nonlinear, non-linearizable, and hybrid systems, and systems beyond robotics that involve molecules. And when I looked at this problem, when I looked at this planning for mission problem, I was very happy at the beginning because I said, you know, we can plan for complex robotic systems using sampling-based algorithms. We know how to do well. We know how to explore the spaces. We should get it. And in fact, several years ago, we are doing much better than we did at the beginning, but with a much more complex scheme than originally expected that looks like this. The low-level planner in the oval is the planners that we use for moving the robots are sampling-based planners, but they are only one small part of the picture that actually has to be inserted very, very carefully in the picture. Otherwise, things tend to break and be very slow. Let me make a small segue to talk about sampling-based motion planners and actually advertise some tools that are coming out of our laboratory that I think are useful to this community. We have lots of sampling-based planners. They either construct roadmaps or they construct trees. Some of you know them as PRMs, RRTs, CSTs, but there are many of them, believe me. And this is just a sample of what exists. And if you want to work with these planners, instead of implementing them, my suggestion is to work with the Open Motion Planning Library. Of course, I'm biased. It's a library that it's an open source planner library coming out of our laboratory. We use this library to show how to implement sampling-based motion planners. We have high-quality implementations of 28 different algorithms, not all of them done by us. 7 are contributed by other groups. It's tightly integrated with ROS through MoveIt, so you can have your sensor data transformed into appropriate planning space. There are plugins available for OpenRave, Blender, Morse, Clamp, and it really shows you the abstractions that are made with sampling-based planners and gives you tools to put these abstractions together, the sampling, the connections, and create new planners. So we do have a number of things to show: planning for the robot, not planning for manipulation. The bottom of the slide shows the connection of the OMPL library with Morse, which is a physics-based simulators. And these are all generated by undergraduate students in our laboratory who like to define their robots and then play games with these robots with physics-based simulation. But what I want to tell this community is that it's amazing that when you see and you collect and you plot statistics and for different performance metrics for the sampling-based planners, you understand what's going on and what is it that you should be using and when is it that you should be using it for planning for a complex robot. And also we can offer a performance measures during runs to be able to evaluate what is happening with the plethora of what we see today called asymptotically optimal planners. So check it out. It is a free library used by many, and send us comments. Help us if you can in promoting this library and in making it more complete. So we had this library, we had these amazing implementations of sampling-based planners that we had used, and we thought, okay, this is going to do the trick. Let's specify things correctly. And for specifying the task correctly, we didn't invent things. We talked with colleagues and we settled on linear temporal logic. Linear temporal logic gives you a set of propositional variables. It gives you Boolean connectives and or not. And for missions, importantly, it gives you temporal connectives like next, eventually, always, and until. And this is a tool that has been used a lot for checking hardware and software properties for very, very large programs. We were happy with it. We settled for a subset of LTL, which is called co-save LTL, that includes only the next, until, and eventually operators. And the reason we did that is that we were told, I mean, with colleagues, and especially by Moshe Varti, who is one of our collaborators in this project, that if you have a co-save LTL formula, you can get a deterministic finite automaton constructed in doubly exponential time, so it's expensive, but this automaton will record all the valid prefixes of your formula. Think about it. You have a very nice encoding of all the valid prefixes of your formula. So our thinking was, well, you have the formula, we convert it to the automaton, we search, we use the automaton as a monitor, And when we get to an accepting state of the automaton, we are done. We have satisfied our specification. So getting from the specification to the low-level planner was what we thought we could do and what many other people in the community are still doing. And then we found that it was slow. This is slow. This, yes, works in theory, but it's extremely slow, and we don't recommend it. We do recommend that you follow, if you want to work with high-level missions and sampling-based motion planners, that you work with a slightly more complex scheme that is shown in this slide that involves this idea of an abstraction, and not a one-level planner, but a three-level planner, a three-tiered planner that has a high-level discrete planner that comes from AI, think about A star, that has a synergy layer that collects information and interfaces between the discrete layer and the continuous layer, which is at the bottom, the low-level planner, which is typically a sampling-based planner. So all this is achieved through this idea of abstraction that I would like to explain to you. But in order to explain this idea, I will use a simpler problem, just going from start to a goal. From start to a goal, yes, we can use the low-level planner, sampling-based planner, but we can enforce an abstraction. In this case, an abstraction is a grid over the space, so you can only move between adjacent cells. It's an artificial abstraction, but I'm just illustrating the idea here. I'm using a discrete search algorithm to find a lead. The lead is in red and shows approximately the dimension in which you want to move. And then I'm passing this information down to the sampling place planner, which is asked to kind of follow the lead, approximately follow the lead. You have to go to our papers to understand what this means. But at the same time, this low-level planner does the exploration, which is shown here in blue, and at the same time, it collects information about the environment that gives back to the synergy layer. The high-level discrete planner weights the graph according to feasibility of paths, and this continues and continues and continues until we get the solution. And we have shown in multiple papers, starting from 2008 up to 2013, that this scheme works well. For the abstraction now, for doing a high-level mission, you have to be a little bit more careful. You have to take the automaton, which encodes all the valid prefixes of your formula, cross-product any abstraction you want to make for the workspace and the robot. And you end up with an automaton. It may be large, it may have thousands of states, but that's okay. It's discrete search. We're not worried that much about it. And if you do the scheme, as I described it before, with the abstraction, which is the cross product of the automaton that encodes your formula and anything that you want about your workspace and your robot, then this scheme works well. And it gives us paths like the paths we expect in a very short amount of time. We're very happy with it. Once we got started and understood the details, I mean, there's a very important issue that comes here, and this is how do you abstract the continuous word? What is it that you need to retain in an abstraction, and how do you use that when you do continuous planning? We understood that this framework is much more powerful than we used it at the beginning. We can have a hybrid system here encoded very nicely, as I will show you. We can extend co-safe LTL by something that many people were interested in, safe LTL, and get more interesting behavior. Safe LTL has the always operator. When we were showing this work, people were telling us, yeah, that's all great, but you know, I always want to have this. I always want to keep away from this area. I always want to be far away from my obstacles or the human. How are you going to guarantee this? So safe LTL was an important thing, and we can have richer specifications. We've shown how the framework works in a number of papers in the last few years. But what's now coming up and is very, very interesting is this idea of partial satisfaction. What if you cannot execute your mission? Should you abort and stall, or should you do something different? So one idea is to satisfy the specification as best as possible, but what does it mean? There's no definition of what this means in LTL. In the same way that we used syntactically co-safe LTL, that is, we had an automaton that accounted all the valid prefixes, we can use safe LTL that has the next and the always operators. So safe LTL, always avoid the obstacles, always avoid that region. You can get a DFA, we found out after some work, that encodes again all the prefixes of the satisfying infinite traces as following. First of all, we negate the safe formula, and we construct an automaton, and this accepts all the violated finite traces, and then we negate that automaton by making the terminal states non-terminal states and vice versa. And this automaton accepts the prefixes of the satisfying infinite traces. So here we can put a scheme together that will work with the following constraints. You have a partially known environment, you have an LTR formula which has a part which is syntactically co-safe and a part which is syntactically safe. And you can have a general robot in there, and you want to find the motion plan that encodes the formula as safely as possible. And this is the general schema that solves the problem. And as I'm showing you to you here, notice that this idea of abstraction, again, is very important. And the fact that we get to an abstract structure that we can search with a discrete planner, and then a synergy layer will collect information about what is happening with the progress of the low-level planner, and will weight that abstraction accordingly. The abstraction, I would say a few more things. If you have a hybrid system, for example, you should be taking that information into your abstraction from the beginning. What we propose is that that we construct an abstraction for the model of the hybrid system that does not have the states only, okay, the states of the environment, let's say, but it also encodes but in its transition relation, it encodes both regional and modal adjacencies. So you see modal adjacency, meaning what are the jumps and what are the guards, how can you transition from one mode of the hybrid system to the other. So the point I'm trying to make with this slide is that this idea of abstraction is very rich. It can encode not only information about the workspace, but more importantly, information about your robot, any properties that you have, or any intrinsic behavior that you know about the robot very, very generally. And of course, you are going to couple this with any information you have for the high-level planning from your LTR formulas. As I said before, the co-safe formulas will give you a nice deterministic final automaton. The safe formulas will give you, again, a nice non-deterministic automaton. You're going to take the cross product of these, cross product of the abstraction of your space and your robot. It's a lot what you end up with, but it's nothing compared to the continuous version of the problem. So you search this discrete structure with your favorite algorithm. You have a suggested sequence of cells that can be followed in order for the system to actually transition to the final state and satisfy the formula. And then you try to see if your planner can execute it. If not, you collect information about progress that is done at that time, and you change the lead, you change your leads until you get to a solution. At the end, the lower planner produces a continuous trajectory that follows a satisfied high-level plan. A plan like this, for example. So what now if you have a door here, and that door is closed, and you wanted to execute that task, but the door is closed? What are you going to do in that case? What does partial satisfaction of an LTL formula mean? We have a problem here because LTL is Boolean. Okay, it doesn't tell you how much you've satisfied things. People didn't care about it. They cared if the arithmetic processing unit, is working correctly or not. But for us, it's different. I understand that we never want to violate safety. But co-safety, well, maybe if you cannot water the plant, that's okay, and you should continue on with your mission. What does it mean to have a partial satisfaction? I don't have time to go into this, but we do have 3 suggestions. Suggestions that never satisfy the specification, very conservative suggestions, moderate suggestions that violate the minimum number of specifications. You have to understand how to find these. Or sometimes we can be very aggressive and allow violation of the specification. What happens when you find a change in the environment is that you have to change your scheme to take into account the change in the environment. But the beauty of this framework, and what makes me believe that there's something interesting behind it, is that when you find a change in the environment, of course you have to execute a guard to an emergency mode, and then you need to have a contingency maneuver always to be able to stop. But then you can locally fix your abstraction. You don't have to start from the beginning, as it is often done in reactive synthesis. Here, you still have a valid co-safe automaton, you still have a valid safe automaton, and the only thing that changes is the abstraction for the environment. The only thing that you have to repair is this abstraction, which is easy to construct. It's not that difficult. And you then take again the cross product, and what? You have traveled to some point, that's fine. You start from that point, and you look at the remaining segment of the specification to be satisfied by working with the new abstraction and using the same kind of planners. So we do have a framework at this point where we can have a hybrid system of complex dynamics, we can have a partially known environment, and we can execute a temporal specification. We still don't understand exactly what partial satisfaction means, but we do understand and we placed a lot of effort in making our abstractions fast and no need to generate everything from the beginning. If you're interested in this, don't re-implement. Check OMPL because we are distributing everything. There are many open issues. Partial satisfaction, stochastic system. We showed some work in Wafer 2014. Multiple robots. There is a paper by Intrin and Saha here in IROS. And the last thing I'm going to say is we are moving a little bit into sketching plus plan outlines and the use of SMT solvers because we think it may be okay for us to specify things approximately. We have a lot of user knowledge when we look at these problems and then get automatically to a formula, to a Boolean formula that will be given to a powerful tool like an SMT solver. So I'm going to finish here. I want to say that there are many, many different things that need to progress in order for us to get to planning for high-level missions. We hope that we're making some progress in this domain, and I want to thank the students and the collaborators who worked on this, and thank all of you for your attention. Thank you.
My name is Tony Deere, and I will be talking about using nonlinear dimensionality reduction for robot locomotion planning. Our motivating example in this talk will be this three-link swimmer shown on the summary slide with joint angles alpha 1 and alpha 2. Now, in robot locomotion, one can often represent maneuvers and motions as trajectories on the shape space, parameterized here by this Euclidean grid in the joint angles. This allows us to talk about certain characteristics of these motions or maneuvers, such as power expenditure. If we were to talk about power expenditure in this case by using the path lengths on the shape space, one may conclude that these two motions shown here have the same power expenditure because the path lengths are the same. However, this is not always the case. For example, if the swimmer is in a low Reynolds fluid, think such as a high viscosity fluid such as maple syrup, in the first maneuver, the arms are effectively fighting against each other. And the drag forces of the fluid actually require you to expend more effort to execute the first maneuver than the second. So we may say that this Euclidean representation of the space is a poor one for representing these external factors. We would like to rectify this mismatch by kind of reshaping or restretching the shape space. Now, this problem of reparameterizing spaces and manifolds sounds a lot like one from nonlinear dimensionality reduction. In this picture, the data shown here are sampled from some underlying manifold, some geometric structure. We may say that this representation of the data is a poor one if we care about looking at distances on the manifold, because geodesics on the manifold, such as this red line, do not actually correspond closely to what we know as the Euclidean shortest distance or the straight line distance between these points. What nonlinear dimensionality reduction algorithms like ISOMAP, for example, are able to do is to reparameterize this data into a space where the Euclidean shortest distances actually correspond closely to the geodesics on the manifold. Now, how can we use this to do our shape reparameterization problem? Well, what our contribution was to do, we started with our Euclidean parameterization. We sampled a uniform grid of nodes on the space to get our input data set that we would use for something like ISOMAP. Instead of using the nominal Euclidean distances between each of these nodes, what we do is we derived a distance metric based on our knowledge of kinematics, drag forces, anything else within the system, to get the distances locally between each of the points on the space. And we were able to feed all of this into ISOMAP and kind of get a new parameterization of the space wherein the original sample nodes were kind of pulled or like relocated into different locations in the space. This gives us a new embedding of the shape space, and you can see here that distances along different diagonals actually have, or the path lengths are actually different, representing the different efforts required. Thank you for your attention, and I hope to see you in the interactive session.
Good morning. My name is Jeff Bingham, and today I will be presenting a method for planning and control for recovery of a fall from a height. And so we can take some inspiration from a house cat, because cats do two very interesting things when they fall. The first is that during midair, they're able to orient without using any external forces. And when they actually land, they use the natural springiness of the neuromuscular state to land softly. So to actually synthesize, my goodness, to synthesize the algorithm that allows for orienting during air and softly landing, we break this up into two pieces. The first, a falling phase, which is to solve a non-holonomic trajectory problem to get a multi-link system from one pose to the next in a fixed amount of time. And then a landing phase, which is to find a landing pose and control that touchdown to minimize the impact contact forces. And since CATs are very complex systems, for the purposes of this talk, we'll be using just a simple planar 3-link mechanism instead, which we've implemented in hardware using a 3-link servo robot sliding down an air hockey table. So the math is a lot of fun, but if you actually want the details, please visit my display. I'll just go over very briefly what the overall hierarchy is. We actually begin in the middle of the process by looking at the impact pose that would minimize the transfer of momentum at contact while maximizing the contact time. Once we have the final desired pose, we can solve from an initial pose a series of configurations that drive the system from the initial orientation to the final orientation. And we can also replan this during while the system is falling or time dilate as necessary to reject disturbances. Upon contact, the joint impedances can actually be set to follow a Cartesian impedance that minimizes the actual contact force, and also to follow a trajectory that causes the system to move into a rolling configuration. If you have any more questions, I'd be happy to answer them during the interactive session. Thank you.
My name is Rashid Alami. I'm presenting this paper on behalf of Perukuti, who was not able to make it. So this paper deals about a reactive motion planner for a non-harmonic mobile robot. So I will briefly motivate and present the specific potential field they have proposed, as well as the control design and some simulations. So while I would summarize here essentially by mentioning that my colleagues have chosen here a reactive motion planner based on artificial potential field, and as we know, potential fields are based essentially on an attractive force towards the goal and repulsive force, and they are proposing a new artificial potential field method, which allows to avoid the local minima by dragging the robot when its orientation is towards an obstacle. Okay. Like so, here is the illustration of this force that drags the robot out of when the speed is inside rectangular regions. So the second aspect of the paper concerns the control method. And what is important here is that now that we have a potential field, the authors mentioned that a P controller is not robust because with respect to disturbances, and they proposed the use of what they call IPID, an intelligent PID controller, to track the desired angle. And generally speaking, this method locally approximates the system by a local model with an unknown term. And this unknown term can be estimated online based on the estimated measurements between input and output. So these are a simulation run, or I would say standard simulation run, which shows that even if the robot is able to avoid obstacles, there are unexpected oscillations in the system. While using their scheme, we can see in the figures that generated forces allow the robot to reach the goal while smoothly and without sudden change yields to smoother controllers. Thank you.
This is spherical parabolic blends for robot workspace trajectories. So, how many roboticists does it take to screw in a light bulb? To answer this question, we need to look at the Cartesian workspace trajectories of the robot. So given a sequence of waypoints, we want to find a trajectory through those waypoints. We want to do this with continuous non-stop motion and with a constant axis of rotation. So a lot of existing methods for workspace interpolation, you could do rotation vector parabolic blends. These give you multiple waypoints, but they can take indirect paths. You could do spherical linear interpolation. This has the compelling advantage of a really cool name, SLIRP, and maybe more importantly, it gives you a constant axis of rotation. But it's only point-to-point, so a single start and end point. Or you could do quaternion Bezier curves. These handle multiple waypoints, but they vary the axis of rotation. So if you take the textbook rotation vector blends, these are going to vary the axis of rotation in each segment, and so take an indirect path to your goal. All right, so to get around this, we propose to combine SLIRP with parabolic blending. Right, the mathematical intuition here is to vary the interpolation parameter over time and near each waypoint to interpolate between the previous and the next segment. All right, so if we do this, then we get our constant axis of rotation in each segment of motion. All right. We can do this on our physical robot. So here we have the shunt robot threading and inserting a screw. Okay, so what we're doing is interpolating through multiple Cartesian waypoints. We have nonstop constant axis trajectories, and there's free code for this on GitHub. So one final note, I want to thank my advisor, Mike Stillman, who passed away after we sent in this work. So thank you very much, Mike.
Hi, my name is Dennis Fassbinder. I'm a member of the Institute for Autonomous Systems Technology at the University of the Bundeswehr Munich. And today I'm going to talk about a paper, Trajectory Planning for Car-like Robots in Unknown Unstructured Environments. Since our focus is on navigation under adverse conditions, we designed an algorithm that is able to deal with unknown, unstructured environments cluttered with obstacles, rough terrain, as well as poor GPS reception, and corrupted, possibly unreachable waypoints. The algorithm was implemented and tested on our autonomous vehicle MUCA-3. It's shown here at the Eurothlon 2013 competition, where it took first place in the autonomous navigation scenario. Our approach uses A*-like search to find a feasible path within the local occupancy grid. The paths are constructed from fixed-length cloplet arcs. What is special about our approach is that while the paths are drawn towards the goalpost by the heuristic function, they are not required to actually reach the goalpost. This is illustrated in the figure below, where the goalpost is shown as a green arrow in the lower right, and the resulting trajectory is shown in green. The following video shows the planner in action on our vehicle MUCA-3. Some of it was filmed from the outside, while other parts were recorded using our onboard camera system. During the whole video, the vehicle is driving completely autonomously. Here you can see it avoiding obstacles at Eurothlon 2013. In the upper left, you will soon see the local occupancy grid, with obstacles shown in red. The global path generated by a higher level planner is cyan or blue, and the resulting trajectory is shown in green. As you can see, it would not be possible to simply follow the global path, since it's very coarse and often leads through obstacles. Apart from obstacle probabilities, the grids also store information such as distance to the closest obstacle, road probability, vegetation probability, height, and slope. All of these features are considered in our cost function, along with the curvature and the rate of change of curvature of the cloth-head arcs that we use to construct our paths. As you can see, the algorithm runs in real time. In the last part of the video, it is shown that the planner can actually be used to navigate more or less completely unstructured areas where any kind of road detection algorithm would fail. It also illustrates nicely that the planner is able to deal with pretty severe GPS offsets. What was not shown here is that you can also use the planner to generate more complex maneuvers and make the vehicle go backwards, for example. If you come to my interactive session, you'll see videos of that. Well, so that's it. Thank you for your attention. And as I said, if you want to see more videos or ask about the details of the algorithm, please come meet me, and I'll be happy to answer your questions.
Good morning, I'm Michael Schoeman from Carnegie Mellon, and I'll be talking to you about trajectory generation for BallBot. So BallBot is a dynamically stable mobile robot that balances on a single spherical wheel. And we think it's a really interesting platform to do research with, one, because it's inherently compliant due to its balancing, and it's also tall and skinny, which allows it to more easily navigate cluttered human environments. We present a method for dynamic trajectory generation that is fast and comes up with feasible trajectories to execute with the BallBot. Here you can see navigation through some obstacles. This method is also starting from arbitrary initial conditions, allowing it to smoothly transition from one trajectory to another if given a goal that is different from the one it was already moving toward. The method is stable up to many hundreds of waypoints and still takes less than 100 milliseconds for trajectories up to 25 meters or hundreds of waypoints. Here you can see a trajectory that goes through multiple rooms, a hallway. We also are using a model predictive control like replanning structure to follow the trajectory, and I'd be happy to give more details about that if you come and see our poster. This method is also fast enough that we can use it for dynamic replanning if the environment changes. So if we're executing a plan that a person maybe gets in the way of the robot while it's on its way to a goal, such as you'll see in the next video here. So here the robot's given a goal in the lower right-hand corner of the frame, and I step in front of the robot, and you can see that the robot smoothly transitions to a new trajectory that respects this new obstacle. So these trajectories start from a kinematically feasible trajectory and then are refined and optimized such that they can be executed by this dynamic system. By using the kinematic plan, first we save a lot of planning instead of going to a high-dimensional state space. So in summary, I'd like to reiterate that this is a method for fast trajectory generation that's stable for very large trajectories, and these are dynamically feasible and experimentally validated on our platform, the BallBot at Carnegie Mellon. I'd be happy to tell you more details about the algorithm and discuss it at length at my interactive session, which is in Salon 4 on Talk 2.7. Thank you very much for your attention.
Hello everybody, my name is Jörg Müller and I'm presenting joint work with Gaurav Sukhatme on risk-aware trajectory generation with application to safeguard auto landing. In autonomous navigation tasks, robots often have to deal with substantial uncertainty of sensors and actuators, resulting in deviations from the desired trajectory. Whenever they navigate close to obstacles, robots should be aware of the corresponding risk of collision. Examples are UAV landing, navigation through narrow passages, and docking. The key challenge in this domain is to minimize the risk of collision while ensuring smooth and feasible trajectories. We present a trajectory generation approach that respects the system dynamics and allows the trade-off collision risk against other properties such as duration and energy consumption. This combines two research areas, namely trajectory optimization and planning under uncertainty. Planning under uncertainty requires an efficient way to estimate the risk of collision when executing a potential trajectory. Due to state estimation errors, the system usually deviates from the desired trajectory, and in this example, it bumps into the landing pad with a substantial vertical velocity. We assume a locally linearized Gaussian system with EKF state estimation and compute the a priori covariance of the deviation from the desired trajectory. Computing the maximum collision-free scaling of this covariance provides an efficient estimate of the collision risk. We use the estimated risk as a weighted cost component of our trajectory optimization. To efficiently represent trajectories in the optimization, we exploit the differential flatness of the system. This representation also takes care of the dynamic constraints. To parameterize flat trajectories, we use polynomials and encode the initial and goal state in the polynomial parameters. This reduces the optimization space from a 12-dimensional continuous function to a low-dimensional vector, which can be efficiently optimized. We evaluated our approach using the task of safe quadrotor landing, where the quadrotor is supposed to land with a low vertical velocity, not to crash a landing gear, on the green landing pad. The state-of-the-art minimum snap trajectory optimization stays close to the collision region and therefore is in high risk of collision. In contrast, our risk-aware approach keeps the trajectory away from the collision region and also minimizes the expected deviation in this area. If we set a higher weight of risk, our approach generates a trajectory that keeps even more distance to the collision region. We can use that trade-off between risk and duration in that case. While the minimum snap approach generates a trajectory with 18% collision risk, our approach results in 0.2% for the same duration and gets even lower if we assign a higher weight to it, risk. I'm happy to discuss all the details with you in the interactive session. Thank you for your attention.
Hello, my name is Feline Donner, and I'm here in behalf of my colleague Alexander Pegorowski, who unfortunately can't make it today. His work is on hierarchical robustness approach for non-prehensile catching of rigid objects. Non-prehensile catching is one of the most challenging tasks within dynamic manipulation because we're not using any force or form closure in order to catch an object, but we use simple flat end effectors to catch. So we need to take the dynamics of the objects into account in order to be able to perform this catching task. For this work, we assume that the object shape dimensions are perfectly known to us. And we use the setup as displayed here on the right. So we have an air hockey table, which is inclined. Through the inclination, we can manipulate the gravity acting onto our object. And we have these 2 or 3 degrees of freedom robotic arms mounted on both sides, which can be used for throwing and catching. Within this work, a hierarchical top-down robustness approach is suggested. On the highest level, we have the decision, followed by the motion planning, and then on the lowest level, we have a robust tracking controller. For the decision level, a norm is introduced. This norm is based on the relation of the object velocity to the end effector velocity. And we can see here in the graph on the right side that the higher the object velocity with respect to the end effector velocity at the point of contact is, the harder it will be for us to perform a direct catch. And in the worst case, the only thing that we can do will be to minimize impact. On the motion planning level, the direct catch is described in more detail in this paper. So the direct catch consists of a multi-phase motion planning problem. At the beginning, we need to predict, from observation, we need to predict the trajectory of the object. Once we have done that, there will be a sequence of motions which makes sure that at the time instant TAP, our end effector will have approached the object in a way that it moves with exactly the same velocities as the object and touches this minimal bounding circle of the object. So from there, we can approach the object, make contact with the object, and after TC, there's the last phase, our balancing phase. And this balancing phase is formulated as a constraint optimization problem with the constraints that we need to make sure that these forces here, you can see F11 and F2 need to be greater than 0 to maintain contact. And we want to minimize the necessary friction we need so that the object doesn't slide on our flat end effector. So we try to minimize our force F12 that's needed. And just a quick video, and I'll be very happy to answer any more questions in the interactive session. Thank you very much.
Chao Hui Gong from Carnegie Mellon University. Today I'm going to talk about parameterized controller generation for multiple mode behavior on a snake robot. So snake robot has many degree of freedom. One effective method to generate motions for such high degree freedom system is to couple its joint trajectories as a sinusoidal function. Then by simply tuning these parameters, we were able to generate a variety of different modes of locomotions on such a high degree freedom system. But one apparent limitation of such a control method is it couples all the joint trajectories and dedicates the entire robot into a single mode behavior. However, it is often desirable we want the robot to simultaneously perform more than one task. For example, in this paper, we consider that the robot perform visual tracking while it is moving along a pipe. So the specific approach we took is we decoupled the mechanism into two different parts, with one part dedicated to climbing the pole, while the rest of the joints will be dedicated to align the head to maintain a constant looking direction. So to generate climbing motion, we use the conventional compound supernoid curve, while to maintain the constant heading direction, we use the joint trajectory optimization to compute joint trajectories to minimize the heading error, avoid joint singularity, and to ensure it can generate smooth and cyclical joint trajectories to synchronize it with the locomoting part of the robot. To avoid compute a numerous amount of joint trajectories per potential looking direction, what we did is we applied a fast Fourier transform-based model decomposition to identify a low-dimensional analytical representation of all these joint trajectories. And what we achieved is we have an analytical representation of these head-looking joint trajectories, and it uses only two parameters to control the heading of the robot. So based on this derived equation, we were able to build a feedback controller to let the robot visually tracking a moving object in terms of these few parameters rather than a numerous number of joint angles. And this approach can be easily generalized to even higher dimensional systems. If you have any question, just come and stop by my poster. Thanks.
Hi, my name is Nelson Rosa, and I'm going to talk about generating walking gaits for underactuated bipeds by having them stand still. This is based on an algorithm developed by myself and Kevin Lynch at Northwestern. Now, underactuated bipeds have the potential, those with fewer actuators and degrees of freedom, have the potential of being more energy efficient, cheaper, and agile than their fully actuated counterparts. And even fully actuated bipeds can become underactuated for various reasons. Why is gait generation hard? It's informative to look at the case of a biped with zero actuation, or passive walkers. Their gaits are very energy efficient, but with zero control authority, you don't design passive gaits, you search for them. The most common way is to use a root solver to find periodic passive gaits. Your inputs are a guess at the post-impact state of the robot and the gait's duration. These inputs have to be near root in order for the solver to converge. Now, to ensure convergence, your best bet is to grid up the n+1 dimensional space and wait until you get lucky. This is pretty inefficient. Our method starts with a counting argument. With n+1 inputs and n constraints, we should expect a one-dimensional branch of walking gaits to exist. And this argument applies for any model. The nice thing about the points in this branch is that they satisfy the dynamics and constraints exactly. Here's an example motion of one of these points for a two-link model. What we want is to find these points, this branch. Equilibria can be used for this purpose. Conceptually, they correspond to your robot standing still. Now, they actually form a pretty useless branch of gaits, those of more just standing around, but at special points, they actually intersect with a walking branch. Time is the only unknown, and our algorithm can handle that. The second take-home message, so there's no more search. The second take-home message is this notion of growing solutions. For example, to add controls, you simply extend the underlying space and treat your passive gaits as part of a larger connected component of powered gaits. And now our algorithm applies to a broader class of bipeds. That's the algorithm in a nutshell. It scales well with the degrees of freedom, and it's extensible with user controls. If you want to learn more, please stop by my interactive station. Thank you.
Hi, welcome everyone. My name is Jacopo Aleotti. I'm from the University of Parma. The title of this paper is Global Registration of Mid-Range 3D Observations and Short-Range Next Best Views. This work is about autonomous robot exploration of unknown objects using a robot manipulator equipped with range sensors. The problem we address is that 3D sensors have a minimum sensing distance. Therefore, the robot should keep such a minimum distance to observe the object. We propose a hybrid 3D sensor fusion system with two range sensors in end configuration. The two range sensors have complementary characteristics. The first sensor is a planar mid-range laser scanner. The second sensor is a short-range camera. In our approach, a first observation of the environment is taken by using the mid-range sensor. Then the robot explores the object in the environment at close range using the next best view planner. Finally, all the object observation are registered together using a global registration algorithm. Here you can see a video that summarizes the approach. In the first phase, you see the robot that takes a frontal view of the scene with the mid-range scanner. We have an environment with multiple objects. And after this phase, we have a point cloud, a raw point cloud, and we extract initial cluster for each object, and then we also build an occupancy grid map for the next phase. In the second phase, we perform a short range observation of each object. In the video in the top left, you can see the motion planning environment. Here we are planning short range next best views using the short range sensor. And in the bottom right, you can see the robot following the planned path. Here, the robot explores all the objects, and for each object, the robot takes many views until there is enough information gain. And an interesting thing to notice is that the robot cannot use the mid-range sensor to look at the back of the object because there is these big obstacles on the back. So the only way to explore the environment is to use close-range observations. At the end of this phase, there is a final registration of the object views using a global registration approach. You can see on the left the point cloud for each object as they have been acquired, and on the right side, the result of the global registration approach. We are using a global registration algorithm that register all the views at the same time. And this is another example. Thank you.
Hi, I'm Rachel Hornung, and I want to talk to you about work I've done at the DLR and the German Aerospace Center and the Technische Universität München on automatic fault detection. In order to ensure high reliability and accuracy of robotic systems, early fault detection is crucial. While it is fairly easy to collect information on valid robot behavior, it is almost impossible to collect data about invalid behavior. On the one hand, we do not want to destruct the hardware, and on the other hand, we are not very sure whether we have covered all possible faults. Therefore, we chose to focus on a data-driven and machine learning-based approach that only needs data of the valid behavior and automatically detects invalid configurations without making any implicit assumptions about the possible errors. Our approach can be used for any system that provides information on the current states, like sensor readings and control commands, and it can be adjusted if improvement is necessary even after the application phase has started. Yet this system does not depend on the latest data history, so it can detect slowly slinking appearances of errors just as well as sudden appearances of faults. In order to achieve this, we use a two-stage approach. After collecting data of the valid robot behavior, we project this data to a lower dimensional manifold. On the one hand, I'm sorry about the wrong projection. I don't know how to switch it in a short time. But you will be able to see a better projection at the interaction section. Anyway, once we project it to a lower dimensional manifold, it is much easier and it simplifies and improves generalization for the succeeding steps. And on the other hand, we also learn a back projection and the typical back projection error to learn the typical back projection error. Then during the application phase, each new data point is projected both ways, and if the difference of the error is too large, the data is considered an anomaly. Now, if the data point is accepted, we still might have an anomaly. So we need to discriminate the valid from the invalid space, which we do with a model that can discriminate known and unknown space from each other using a support vector machine. We have tested this approach on simulation and real data recorded from a robot. And as you can see on that graph, we can detect collisions very accurately or faults very accurately while not having many faults. Thank you.
Hi, my name is Tomas Lozano Perez. I'm from MIT. This is joint work with Leslie Cabling. The problem that motivates us is to connect at a high-level symbolic task planner that can plan long sequences. For example, say make dinner and you get a sequence, but then ultimately that has to be executed by a robot, so we need to actually plan the individual motions. Now, the fact is that these constrain each other. That is, a plan needs to consider the motion, whether the motions are going to be feasible, and the details of the motions need to achieve the high-level plan. The approach that we're pursuing here starts by it's considering the idea of separating the task plan in terms of sequences of actions with variables in them. These actions are sequenced based on causality, whether they cause the desired effects. But there are these geometric variables that are left open. Then there's a separate process that is going to choose the values of the geometric variables. Now, as I've just said, these variable values are constrained because of the environment and the plan. So what we need is a mechanism for effectively choosing them. Now, the thing that is hardest is the fact that the constraints can arise quite far in the plan. For example, here's a sequence in which we want to put the blue object in the middle region, which is constrained. Now, the grasp that is feasible at the end, when we actually put the object, is going to affect what we do before that. In this case, there is no we can't grasp it that way at its current location, so there's going to have to be a regrasp in between. So these constraints can propagate throughout the plan. Here's another example in which we're putting two objects into a constrained region, and the idea is that you have to put one in the back and one in the front. So the way we do this is using a discrete CSP planner. This is a technology from artificial intelligence constraint satisfaction problems, which involves backtracking search and constraint propagation. And we've developed a sequence, a kind of little language of constraints of 3 or 4 types in which we can represent the conditions that arise during typical manipulation plans. And then the variables that are explored are constrained to be discrete but finely sampled, and the constraint satisfaction planner searches over these to try to find sequences of variables that satisfy all the constraints. Thank you for your attention.
Good morning. My name is Nicola Bezza, and I'm a postdoc researcher at the University of Pennsylvania. Today I'm going to present the work that I've been doing together with my colleagues at Penn on attack resilient state estimation for autonomous robotic system. The motivation for this work can be found in this slide, in which I gather a bunch of news that you can find and download from the web, and that show how recently hackers were able to hijack the compromised complex system simply by spoofing the sensor, actuator, and the communication of the vehicles. Example of systems that are compromised are power plant, drones, and even the car that you drive every day. So the problem that we're interested to solve is under malicious attack on sensor, on a vehicle like, for instance, this Lancia robot, we would like to be able to estimate the correct state while it's performing a certain task, for instance, waypoint navigation, cruise control, or obstacle avoidance. We would like to be able to consider sensor noise and also build a recursive implementation that is more suitable for hardware implementation. Our strategy, which we call a recursive adaptive estimator, leverage the linear quadratic estimator, in which, together with the predict and update steps, we add a shield step that increases the error covariance of a measurement that is detected that is compromised. Here are some of the formulation that we use. We start with a model of a system, then we run a prediction, and in the update phase, the Kalman gain is modified by adding the shield gain that has this form. During the interactive session, I will also show you the introduction to the attack to noise ratio, that is a metric that we use to prove existing expectation evolution of this shielding gain. Our strategy was validated via software and hardware implementation for each on different platform. For each platform, we extract a model and then we run like a simulation in both ROS and MATLAB. So what you see on the bottom of this page are some snapshots of some of the results that show how the state is able to converge to desired value even when some of the sensors are compromised by attacks. Okay, here I show you some of the implementation that we run on both ground vehicles and a car. And specifically, here's a cruise control case study in which both vehicles need to maintain a desired speed even when some of the sensors are compromised. The GUI that you see on the top right was used to attack the sensor, and what you see is that both vehicles are able to maintain the desired speed, even when some of the sensors are compromised. For instance, here the encoder was compromised. Okay, thank you for your attention. I hope to see you during the interactive session that show you more results and more video, including also some preliminary implementation on quadrotors. Thank you.
Hi, I'm Chad Kessens from the United States Army Research Laboratory, and I'm here to present a metric for self-writability and understanding its relationship to simple morphologies. A few years ago, I had the opportunity to take an Army training course where I learned that one of the major problems that soldiers face is when the robot tips over. In this situation, it can be very difficult, even for a skilled operator, to return the robot to its normal operating orientation. After reviewing the literature, I embarked on a program with two goals. First, to maximize a generic robot's ability to autonomously self-write, thereby allowing us to retrofit existing fielded systems, disparate as they may be, but also enabling us to apply the technology to future systems, no matter what they may look like. The second goal is to inform that future robot design, allowing us to create robots that are better able to write themselves. In this paper, we specifically addressed the second of these goals. First, we created a self-writability metric for design evaluation, and then we demonstrated the application of that metric across multiple design parameters. First, a brief review of our framework. We begin by plotting the robot's conformation space map comprised of all joint configuration and body orientation combinations for which the robot is stable. This map is naturally divided into various conformation subspaces which are continuously connected. Each of these subspaces can be represented as a node in a directed graph, and each node has an associated volume related to the quantity of stable states contained within. Our metric simply takes the total volume of stable states that can reach the goal and divide by the total volume of states within the map. We then applied this metric in three ways. First, we demonstrated the principle with a simple range of motion study. Here you see the conformation space map for two identical robots, except the lower one has a range of motion 15 degrees larger than the top one. Plotting our self-writability metric versus ground angle shows that this larger range of motion re-enables a key transition in the map for a large number of ground angles, significantly improving performance. Next, we performed a design study for the notional vehicle pictured in the upper left. Using 2,000 different samples of different designs covering 6 parameters, including joint range, body chassis aspect ratio, ground angle, limb mass, mass location, and limb length, provides some insight into general design principles. Finally, we applied the metric to help us tune the arm mass for a physical 3 degree of freedom robot. I'd love to talk more about this with you, and I hope that you'll stop by my salon for the interactive session. Thank you.
Hi, my name's Troy McMahon, and I'm going to be presenting the work from the paper Sampling-Based Motion Planning with Reachable Volumes, Application to Manipulators and Closed Chains. The problem addressed in this work is the problems of motion planning for highly constrained systems and motion planning for high degree of freedom problems. High degree of freedom problems are problems in which there are hundreds or even thousands of degrees of freedom in the robot. And this is applicable to problems such as protein folding. Constrained systems are systems where it could require something like a robot to maintain a certain orientation or maintain contact with the object. And this is a difficult problem because the probability of randomly generating samples that satisfy a constraint could approach zero in cases where the constraints are a manifold. What I presented in my previous work is called reachable volumes, which encodes the relative positions that the joints and end effectors of the robot can occupy. And I presented a method for computing reachable volumes in a sampler based on reachable volumes, which is applicable to high degree of freedom problems and problems with constraints. And here you see methods for computing the reachable volumes and an example of generating a sample using the reachable volume sampler. This work and this place I present a couple of complexity proofs for reachable volumes. I showed that the complexity of reachable volumes of the reachable volume sampler is linear for problems without constraints, and I present an O of 1 data structure for representing reachable volumes in problems without constraints. I also perform an extensive experimental evaluation of reachable volume sampling, which is the red in this example. And I show that reachable volume sampling is more efficient than the existing methods, particularly for higher degree of freedom problems. I show it's applicable to a wide variety of constrained systems. I show it's capable of producing better connected roadmaps than existing methods, and that it's capable of solving a number of environments and that other methods can't solve. So please come to my interactive session. Thank you.
Hi, I'm Tobias Kunz. I'm presenting our work on probabilistically complete kinodynamic planning for robot manipulators with acceleration limits. This is work I did with my advisor, Mike Stillman, who sadly passed away after we submitted this work. Sampling-based planners, like for example RTs, have been very successful in geometric domains where only joint positions are considered. But because those geometric planners do not consider joint velocities or differential constraints, they cannot handle problems that have non-zero start or goal velocities. One example for such a problem is online replanning, where we possibly have a non-zero start velocity because the robot is already in motion. The problem we are going to consider here is that of hammering, where the hammer needs to reach a nail at a high velocity in a certain direction. And as you can see, the geometric planner is able to reach the nail, avoiding the obstacle, but it doesn't reach the nail at the correct velocity and is unable to drive the nail into the wall. Unlike geometric RTs, kinodynamic RTs can consider joint velocities and arbitrary differential constraints, for example, torque limits. However, for high-dimensional problems like the robot arm here, the standard kinodynamic RT using a Euclidean distance function is not very efficient. For this problem, for example, I aborted the algorithm after 1 million samples and more than 8 hours of runtime. In addition, we have shown recently that kinodynamic RTs are not always probabilistically complete. So we propose acceleration-limited planning as a middle ground between poor geometric planning on one side and planning with full dynamics on the other side. Instead of considering joint torque limits, we simplify the problem by considering joint acceleration limits. Our RT planner is very efficient and solves the hammering task, requiring in average only 40 samples and only 56 milliseconds. This is an improvement of about 5 orders of magnitude. Our planner uses a steering method as distance function within the RRT This steering method is able to solve the two-point boundary value problem very efficiently. It can connect two states such that acceleration and velocity limits are satisfied, but obstacles are ignored. And I'm happy to share more details on this in the interactive session. Thank you very much.
Hi, I'm Alan Millard from the University of York, and I'm here to present our paper titled Runtime Detection of Faults in Autonomous Mobile Robots, based on the comparison of simulated and real robot behavior. So there's been an assumption for a long time that swarm systems are robust, in the sense that the failure of individual robots will not significantly affect the collective behavior. And this is true in the case of complete failure, but when we get partial failures, like for example when robots' motors fail, this can negatively affect the overall collective behavior. So we need an active approach to solving this problem of partially failed robots if we ever want to build large-scale dependable swarm systems. So in order to detect the faults, we compare the observed behavior of the real robots against a model of their expected behavior. And in our approach, this model consists of a simulation of the robot controller situated in its environment. And we use a tracking system to observe the behavior of the robots in the real world. So each robot has a copy of every other robot's controller code, which they instantiate within an internal simulator. On the left, you see the real-world scenario, and on the right, you see the internal simulation. And the simulation is initialized such that it reproduces the scenario in the real world. We then run the simulation for a short period of time to predict the future state of the swarm. We can then compare this prediction to the observed state of the robots in reality. And if there's a significant discrepancy between the predicted and observed behavior, then this may indicate that a robot has developed a fault. So implementing this on a swarm system is non-trivial. So to start with, we've done it on a single robot system, which is the focus of our paper. We've used simple obstacle avoidance as a case study. In particular, we attempted to detect motor failure in the form of a slow wheel, which causes the robot to veer off to one side. And the main problem with this approach of using a simulator is that drift occurs between simulation and reality over time due to the reality gap. The longer you run the simulation, the greater the drift becomes, and it causes an increase in the number of false positives. However, you want to run the simulation for longer because it makes it easier to detect faulty behavior, because the trajectories diverge and it increases the number of true positives. So we have this trade-off between minimizing drift due to the reality gap and maximizing divergence of the non-faulty and faulty robot behavior. So in order to prevent this drift getting out of hand, we periodically reinitialize the simulation. And the main contribution of our paper is that we found there exists this sweet spot for the reinitialization time period, which gives us the most reliable fault detection. So if you have any further questions, please come and find me in the interactive session. I'll be more than happy to go through the details of our paper with you. Thank you for your attention.
Hello, my name is James McMahon. I'm at the Naval Research Lab. I'm also a PhD candidate at the Catholic University of America, and this is the work that I'm doing with my advisor, Dr. Aaron Plaku, on a combined motion and task planning framework. So our motivation is to develop a planning framework that reduces the cognitive workload of the user by specifying missions using high-level tasks. We also want to incorporate high-dimensional mobile robots with nonlinear dynamics that operate in complex environments. The key challenges that we face are the robot dynamics and collision avoidance, and the complexity of the tasks that we specify. We also have to face the challenges posed by the dependencies by the combination of the two. So to reduce the cognitive workload of the user, we structure missions using linear temporal logic. LTL combines propositions such as safe, obstacle detected, verbs such as inspect and avoid with logical and temporal operators, and or not, eventually, until, and always. This allows us to specify missions using high-level tasks in a natural, structured language. LTL also provides us with a mathematical framework with which to express our tasks. The proposed framework used in this paper leverages model checking to introduce a discrete abstraction for high-level search. By specifying tasks using LTL, we can construct a discrete finite automaton to be used with a workspace decomposition to provide a simplified planning layer that guides the expansion of our robot's motion tree using sampling-based motion planning. By creating equivalence classes between the motion tree and the discrete abstraction, we cast the planning problem as a search through the motion tree to find low-cost, dynamically feasible, collision-free trajectories to accepting automaton states. The technical contributions of this paper are in the discrete abstraction obtained by combining the automaton with the workspace decomposition, the partitioning of the motion tree into equivalence classes as induced by that abstraction. Here's the costs that estimate the feasibility of reaching and accepting automaton state from each equivalence class, and the multi-objective selection of equivalence classes based on a number of factors. So experiments are conducted on high-dimensional mobile robots operating in complex environments. Several missions are evaluated covering different LTL task specifications. The planner shows both a reduction in running time as well as path costs when compared to related work. I look forward to discussing this in further detail with you in the interactive session. Thank you.
University of Salerno. This is a joint work with the other two colleagues from Italy, and it's about distributed fault detection and recovery for networked robots. So let us consider a team of several robots, and we are in the very general case that the control input of each robot depends on the state of all the other robots in the team. This allows for complex missions. However, neither we have a control, an all-to-all communication or a central unit. In addition, as it happens in real domains, one or more robots might partially or totally fail. So we need to detect and isolate faulty robots in order to start a recovery mission and a complete recovery strategy and complete the mission. These are the assumptions. We consider a first-order dynamics for each robot, and the input is represented by an additional input that is 0 in normal conditions. And the communication among robots is modeled by connectivity graph, and we assume to have a fixed, directed, strongly connected topology. This is a schema of our solution that actually is running on each robot. We have a global observer that is able to estimate the state of all the other robots in the team as required by the controller for the computation of the control input. And it is a consensus-based filter. Then we consider two types of faults. For recoverable faults, we designed a local fault recovery strategy that consists in estimating and compensating the fault on a local base. And in this case, the fault is not seen by the other robots in the team, so the mission does not need to be rescheduled. Then also we consider unrecoverable faults, like, for example, motor breakage. In this case, the other robots need to estimate, to detect and isolate the faulty robots in order to reschedule the mission, also without an all-to-all communication with the faulty robots. What we provide in the paper we provide the convergence for the global observer error, and also we provide sufficient conditions for the detectability of both recoverable and unrecoverable faults. And also we show how our solution is able to detect and isolate also simultaneous faults. We have run experiments on a 5-robot setup, and to see the results and the video of the experiments, you have to come to our desk where also we can talk about details. Thank you.